Good morning, students. Today we will take up the second part of the ethers and epoxides, and this part is about the reactions of unsymmetrical ethers. So it is basically about the reactions of ethers. So before starting with the lecture, I would like to brief you all about the previous lecture that we studied about ethers and epoxides. So in the previous lecture, we studied about various methods of preparation, chemical reactions. So there are three different kinds of reactions. Reactions where the ethereal oxygen atom is involved. Then there is reaction where there is cleavage of the carbon-oxygen bond is involved. And then the third one was the reaction where the alkyl groups, ROR, the alkyl groups are involved. So among the alkyl group reactions, there was auto-oxidation or the peroxidation where the peroxide is formed. And the second part was about halogenation. So where halogenation happens at the alpha carbons, alpha hydrogen. So alpha hydrogen gets replaced by a halogen atom. So let us see some of the other reactions of the ethers. So we will study of when the ethers, till now we were studying when the ethers were symmetrical. Now we will study when the ethers are unsymmetrical. That means the ROR. So one of the R alkyl group is different from the other R group. So there will be ROR dash. Now, unsymmetrical ethers means when the alkyl group is either primary or secondary, then what kind of reaction happens when the alkyl group is primary or secondary, then SN2 reaction, biomolecular nucleophilic substitution reaction happens like it usually happens in case of SN2 reaction. You know that the primary or secondary carb cations, which are formed, they are formed in SN2 mechanism, and we know that SN2 mechanism, it occurs in one step and there is one transition state involved. Now, the important thing about the SN2 reaction is that the nucleophile, it will attack the least substituted carbon of the oxocation. So first, for example, this is CH3O, C2H5. This is an unsymmetrical ether. Hi reacts with it. So the H plus will add on the oxygen atom such that the oxocation that is formed, it further reacts with the nucleophile such that the hydrogen atom of the least substituted carbon will get substituted by the iodide group. So there are two possibilities: either ethyl iodide can form or methyl iodide can form. So here in case of SN2 mechanism, methyl iodide will form and the other will be ethyl alcohol. Now if at this stage we add excess of Hi, then what will happen? This alcohol which is formed, it will further get converted to its respective iodide, that means ethyl iodide. Now, the other condition is when the alkyl group of the ether is tertiary. So then the SN1 mechanism will happen. Now the mechanism is given over here. So one of the alkyl group is primary and the other one is tertiary alkyl group. So Hi will add such that the H plus of the Hi will add on the oxygen atom. It will form an oxocation. Then this further reacts to form a tertiary carb-cation. Why? Because it is more stable. So the more stable the carb-cation, the faster it is formed. And then this carb-cation then reacts with the nucleophile part of the attacking reagent, that means iodide. So it will form tertiary like butyl iodide. So the mechanism is SN1 reaction. Now, when the alkyl group, one of the R group is an aryl group. So it might be alkyl aryl ether. So in that case, what will happen is that the product will always be phenol. That means the H plus will go to the larger group, that is a phenoxide ion. For example, here example is given of anisole. Anisole means a benzene ring with a OCH3 group. So when this reacts with Hi, then intermediate will be phenoxide ion. Now there are two possibilities. There could be replacement of there could be iodide, like phenyl iodide can also form, like C6H5I and then CH3OH, methyl alcohol can also form. But in this reaction, what we have to remember is that it is always phenol which is formed. Next, we come to epoxides. So what are epoxides? Epoxides, like I told briefly in the previous lecture, so all the cyclic ethers, they are called as epoxide, especially the three-membered cyclic ether. It is also called as oxirane. So like ethylene oxide, that is called as epoxide. That is oxygen. When it is a five-membered ring, it is including an oxygen atom. It is called tetrahydrofuran. When it is a it is a six-membered ring and then there are two oxygen, it is called as 1,4-dioxane. Now we will see how to prepare this. So there are two methods given. I would prefer that you go for the upper one, the top one. Uh, the below one might be difficult for you to understand. So the easier one you understand, you know remember. So one is by the oxidation or the epoxidation of the alkene. So when an alkene, it reacts with per acid. Per acid is like, see, so there is benzoic acid, or I mean carboxylic acid, like CH3COOH or CH5COOH. When there is additional oxygen atoms, so instead of two oxygen, there are three oxygen atoms, then it becomes not a carboxylic acid but a per acid, like perbenzoic acid, metachloro perbenzoic acid, trifluoro per acetic acid. And there is a solvent, another solvent like dichloromethane or CCl4, etc. Then what happens is that one of the extra oxygen of the three carb oxygens, one of the oxygen atom, it attached a double bond and it forms the epoxide. And so the byproduct is a acid, carboxylic acid. Now we see the mechanism also, it is given over here. It is very simple, you can just go through it. Next is from halohydrin. So halohydrin means halogen and a halogen atom and a hydroxyl group. So when there are two functional groups, so one is a halogen atom, other is the halogen like a Cl group or a halogen atom and a hydroxyl group. Just a minute. Sorry. So what happens is that, so when such halohydrins, they are treated with a base like NaOH or KOH, then what happens? Then HOH, I mean HCl, it will get removed and the product is ethylene oxide or the epoxide. So of the two functional groups OH and Cl, HCl gets removed and both the carbon atoms, they get attached through the oxygen atom and it forms a tri-membered, like a three-membered ring or a oxygen or an ethylene oxide or epoxide. So if we see the mechanism, so first what the base does, it basically releases the H plus or the proton from the hydroxyl group. And then what happens to maintain electrical neutrality, the chloride atom from the adjacent carbon also goes taking the oxygen's negative charge, and then the bond between oxygen atom and the other carbon atom it forms, and it forms ethylene epoxide. Now let us see some of the chemical properties of epoxides. So we know that it is a three-membered ring and a three-membered ring. So the angle would be between two. The angle would be, and it will be around 60 degree. Now we know that normally the tetrahedral bond angle, because the hybridization is sp3, so the bond angle is 109.5 degree. So there is lot of angle strain in the ring. So to release the strain, the epoxide ring has the tendency to open up. Why? So as to become more stable. So there are two possibilities. This ring opening can be either acid catalyzed or it can be base catalyzed. Acid catalyzed means the catalyst is H plus. Base catalyzed means that there is the catalyst is a base or a nucleophile. Now let us see the acid catalyst reaction. For example, ethylene epoxide, it simply reacts with water in presence of H plus because it is an acid catalyst reaction. So what happens is that the bond cleavage takes place and two OH group. So it's ethylene glycol is formed. If we use HBr, then H plus goes to the oxygen atom, the bromine to the adjacent carbon atom. So it will become ethylene bromohydrin, right? Chlorohydrin, this becomes bromohydrin. Then if we use ethanol as the reagent in the presence of an acid, then it forms 2-ethoxy-ethanol. The mechanism is SN2 mechanism. Base catalyst reaction is also similar. You can just go through it. It's just that the catalyst is a base, like sodium alkoxide or ammonia or amine. The only thing is that the nucleophile, it will attack the less hindered site. Now this is a very small reaction, that is molecular rearrangement. So ethylene epoxide, that means the oxyrene, when it is heated, then it rearranges such that acetaldehyde is formed. So this is a molecular rearrangement reaction. Then we will see how do they react with Grignard's reagent and organolithium reagent. So the mechanism is like very much similar. So there is carbon oxygen bond. We know that oxygen is slightly negatively charged, carbon is slightly positively charged. If we see the Grignard's reagent, it is RMgX. So MgX part is positive and the alkyl group is negative. So the negative alkyl group will go to the carbon atom, the MgX part will go to the oxygen atom. Further, it gets hydrolyzed, and so this intermediate, it is the addition product. This addition product, it gets hydrolyzed and it forms primary alcohol. Okay. Similar is the reaction with organolithium compounds also. Now we come to a very important topic, that is crown ethers. So see, what are crown ethers? So they are basically polyethers having crown-like structure. Since they're polyethers means they have more than one OCH2CH2 like group. So more than one ethereal functional group. So that is a polyether. And in crown ethers, the repeating unit is OCH2CH2. So you can see over here below, all the repeating units are OCH2CH2. Now, if you see the properties, so they form stable complexes with metal ions. Then if you see the applications, they are involved because the crown ether is such a structure that the cavity that is formed out of this crown structure, that cavity is of particular dimension. So it will let an ion, a cation of a particular dimension or a particular diameter get fixed or get trapped inside it. Now, the most important part that is to remember about crown ethers is the nomenclature part. So we have to name it such that, see, we have to see the whole structure, the whole ring structure, and we have to first count total number of carbons plus oxygen atoms. So that will come in a square bracket. So for example, let us see the smallest one, the rightmost. So there are 4 oxygen atoms in 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 carbon plus 4 oxygen. That means 8 plus 4 is 12. So we will put 12 in bracket followed by the term crown dash. Then the number of oxygen atoms in the ring, that is 4. So this structure will be 12 crown 4. Similarly, the one in the middle, you see 5 oxygen atoms and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 carbons plus 5 oxygen, that means total 15 atoms. So bracket mein 15 crown dash 5, because 5 oxygen atoms are there. Similarly, the largest one, you see there are 6 oxygen atoms and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 plus 6, 18. So 18 crown dash 6. Why? Because 6 oxygen atoms are there. Like I told before, why are they called crown? Because their molecule have a crown-like shape, and the bracket number, it represents a ring size, in the terminal carbon, sorry, the terminal number, it gives a number of oxygen atoms. And usually the oxygen atoms, 2 oxygen atoms are separated by CH2CH2 group or 2 carbon atoms. So here the structure of 18 crown 6 is given. So you see that M plus kind of ion, it gets trapped in it and forms bonds with the oxygen atoms. Now, the question arises, for example, if you are given a question that the diameter of this 18 crown 6, the cavity diameter is around 2.6 to 3.2 angstrom, and you are given 3 ions. One, that is sodium ion, it has a diameter of 1.9 angstrom. Another one is potassium, which has a diameter of 2.66 angstrom. Third one is cesium ion, Cs plus, which has a diameter of 3.34 angstrom. Now you are asked which of these 3 will give the best fit with the 18 crown 6 molecule. So you have to see which one matches with the diameter of the cavity. So the diameter of the cavity is 2.6 to 3.2. And all these 3 ions have, among these, potassium ion has the nearest diameter, nearest matching diameter, that is 2.66 angstrom. So this ion will give the best fit. There are certain points to remember about the crown ethers and cryptates. So here I have given the gist. You can just go through it. This is basically for your notes. So this was, first of all, the crown ethers was given by Pedersen in 1967. Now we know that in ethers, the oxygen atom, it has a lone pair of electron. So it can donate that lone pair. That is why it acts as a Lewis base. And the metal ion, it is electron deficient, so there will be ether metal complex. This is the principle why this cavity and this like host and guest relationship is formed. Okay, so you can just go through it. Now, how it was prepared, like I told, it was prepared by Pedersen in the laboratory. So there are 2 methods given. You can Take anyone. Application, like I just told, it is for used in the formation of host guest complex, that is inclusion compounds. Then these are used as catalyst, and they are also used as inorganic solvents also, and then in racemic mixtures also, and then many substitution and elimination reactions. So this was pretty much about ethers and epoxides. I will just take a minute to change my slide. So I just wanted to actually take some very important topic on the carboxylic acid derivative, sorry, which I missed out before. So this is just last part from this unit, and this then we will finish off with this unit. So I've named it carboxylic acid derivatives part 2. So there is one topic, that is nucleophilic acyl substitution reaction. So what is nucleophilic acyl substitution reaction? See, what happens is that all the acid derivatives that we have studied, so there is acyl acetyl chloride, RCOCl, no, acyl chloride, then amide, amine, anhydride, ester. So they all can be interconverted by which mechanism? Nucleophilic acyl substitution mechanism. What is this mechanism? In this reaction, the nucleophile, it adds to the carbonyl group, forming a tetrahedral intermediate, and then followed by elimination of the leaving group, which regenerates the carbonyl group. So nucleophile, a nucleophilic acyl substitution, they are also called as acyl transfer reactions. Why? Because they transfer the acyl group to the attacking nucleophile. Now, if we see the mechanism, you see, in general, if you see any acid derivative, so it is RCOY. Y can be any other molecule which gives rise to the different five different derivatives. So what happens is, like first I told, the nucleophile first attacks. So nucleophile is attacking, so it becomes a tetrahedral intermediate. Then the the leaving group, the Y group, it leaves or it is eliminated. So first nucleophile gets added, then the leaving group gets eliminated. So there is first addition, then elimination. That is why it is an addition elimination reaction mechanism. Now to see which one, like if you compare all the Y's, all the leaving groups, so which among all the 1 2 3 4 5 5 derivatives, which one will leave it faster among all the leaving groups? So we have to see that acid chloride, like we have also I think studied during the carboxylic acid presentation also, that acid chloride is the most reactive among all the acid derivatives. Why? I told before also, because the chlorine group, it is a very good leaving group. Now, see, this tendency for this addition, elimination, and this nucleophilic substitution reaction, nucleophilic acyl substitution reaction, it depends a lot on the nature of the leaving group. So if it is a good leaving group, it will leave faster and the reaction will be faster, and the acid derivative will be eventually more reactive towards that reaction. If the leaving group is a bad leaving group, like amide group, so what will happen? It will not let the reaction happen, and that's why the reaction will be slower and the acid derivative will be less reactive. So if we see and compare the tendency of the leaving groups, the ability of the leaving groups, so we find that the acid chlorides are the most reactive, followed by anhydride, followed by ester, and least as amide. Now, keeping this in mind, we have to see how can we interconvert all of these acid derivatives among one another. So you see, we know that since there is a difference between the reactivity of the acid derivatives, so it becomes possible to convert more reactive derivative to a less reactive one. Why? Because the more reactive it is, the faster it will react. The less reactive, it will be more stable. So the more reactive will give a product which will be more stable. So keeping this in mind, we find that acid chlorides, they being the most reactive, they can be converted into any of the other derivatives. So acid chlorides can be converted to the less reactive anhydride or ester or amide, but the reverse cannot happen. So the most reactive is acid chloride, followed by anhydride, followed by ester, and followed by amide. So acid chloride can be converted to any of the three. Then anhydride can be converted to ester or amide. Ester can be converted to amide, but reverse cannot happen. So amide can neither be converted to ester nor anhydride nor acid chloride. Same. But anhydride, because it is more reactive than ester and amide, so it can be converted to them. But Since it is less reactive than acid chloride, so the reverse reaction, that means anhydride to acid chloride, is not possible. Okay, so with this we understand that more reactive derivative can be converted to the less reactive derivative. Now we see how can the acid chloride can be converted to all the derivatives. So here a reaction is given where acid chloride, it reacts with acid, carboxylic acid. And then the first step is what? Addition of the nucleophile. So it adds. Second step is elimination of the leaving group. So this chloride group, it leaves, and the product is anhydride, and the byproduct is HCl. Same thing is given at the bottom. Similarly, when acid chloride, it gets converted to ester. So to prepare ester, acid chloride has to react with alcohol. So first the addition of the nucleophile, that is OH group, it will get added, and then on the carbonyl carbon, and then the Cl group will be leaving, and then followed by a loss of a proton to maintain electrical neutrality. So HCl will be formed as a byproduct, and we get the product as ester. Again, there is a tetrahedral intermediate involved. Similarly, acid chloride to amide, if we want to see. So for converting it to amide, what we have to do, we have to react the acid chloride with the amine. So first the addition will happen, then the elimination will happen, tetrahedral intermediate will be formed, and then elimination will happen, followed by loss of a proton, and we get amide. So ammonia, if we use as the reactant, then we get primary amide. If we use primary amine, then we get secondary amide. If we use secondary amine, we get a tertiary amide. Then we have to see anhydride to ester. So anhydride, it reacts with alcohol, and it will form tetrahedral intermediate, followed by elimination of the leaving group, and then loss of a proton, and we get an ester as the main product. Then I had anhydride to amide also. Similarly, anhydride when reacts with amine, then there will be first the addition of the nucleophile of the amine group, and then elimination of the leaving group, and then loss of a proton, and then finally we get the product as an amide. So we have to remember that if we use ammonia, then it will give primary amine. If we use a primary amine, it will give secondary amide. If we use secondary amine, it will give tertiary amide. The last one is the ester to amide. So ester when reacts with the amine, primary amine, then it will give respective amide. So here the condition is that the nucleophile that is reacting, it should either be primary amine or ammonia. And this reaction, practically, if we see this reaction takes a bit of time, so it requires prolonged heating for this reaction to happen. This you have to remember. So that's all, student, from my side. If you have any questions, do let me know. Thank you.